What if the universe hides its greatest secrets not in the carefully planned observations of scientists, but in the glitches, the mishaps, the moments when everything goes wrong? Picture this: a researcher adjusts their telescope, hoping to capture a routine image of a distant star cluster, only to find something impossible staring back at them. A shape that shouldn't exist, a light that defies physics, a signal repeating in a pattern no natural phenomenon could ever produce. These aren't scenes from science fiction. They're real, documented moments where human error collided with cosmic mystery, revealing discoveries so astonishing they shattered our understanding of space itself. This is the story of 26 unthinkable finds, each one stumbled upon by pure accident. Think about that for a second. Some of the most groundbreaking revelations in astronomy weren't the result of meticulous planning or billion-dollar missions. They were happy accidents, cosmic typos, where a telescope malfunctioned, a lens was pointed in the wrong direction, or data was misread. And yet, these errors uncovered phenomena that left even the most seasoned astronomers speechless. Unexplained celestial bodies drifting where nothing should survive, strange structures that seem almost artificial, glimpses of forces and energies we still can't fully explain. The universe, it seems, loves to surprise us when we least expect it. So how do these accidents happen? And what do they tell us about the vast, uncharted wilderness of space? Buckle up, because we're about to dive into the most jaw-dropping cases where telescope errors led to mind-bending discoveries. From a star that shouldn't burn to a galaxy that defies the laws of physics, these aren't just curiosities, they're clues hinting at realities beyond our current comprehension. And the best part, every mistake, every wrong turn, reminds us that the cosmos still holds endless mysteries waiting to be found. So let's begin this journey together, where even the errors light the way to something extraordinary. The first discovery on our list sounds like something straight out of a cosmic ghost story, the case of the phantom galaxy that wasn't really there. Imagine the excitement when astronomers first spotted what appeared to be a previously unknown galaxy lurking in their data. There it was, faint but unmistakable, a smudge of light where no known celestial object should exist. Researchers scrambled to confirm the find, only to watch in disbelief as their discovery evaporated under closer scrutiny. The culprit, a glitch in the telescope's calibration system, had created a digital mirage, a trick of the light so convincing it fooled even seasoned experts. This phantom galaxy wasn't just a one-off fluke. It exposed a haunting reality. How often do our instruments deceive us? In the vast, noisy sea of cosmic data, false signals can masquerade as groundbreaking finds. The incident forced astronomers to confront an uncomfortable truth. Even the most advanced technology isn't immune to error, but here's where the story takes a fascinating turn. Instead of dismissing the mistake, scientists turned it into a lesson. They revamped imaging protocols, adding layers of verification to weed out similar illusions in the future. Yet the bigger question lingers. If one ghost galaxy slipped through, how many others might still be hiding in plain sight? Could some of the universe's so-called mysteries actually be shadows cast by faulty equipment? This discovery didn't just correct a technical hiccup. It reminded us that the line between breakthrough and artifact is thinner than we'd like to admit. And in a universe as vast and enigmatic as ours, sometimes the most valuable discoveries aren't the ones we make, but the illusions we learn to see through. Now let's talk about a cosmic heartbeat that nearly rewrote the laws of physics, until scientists realized they were listening to a glitch all along. It started when a radio telescope detected a pulsar, one of those dense, spinning stellar remnants that flash like celestial lighthouses. But this one was different. Its pulses arrived in a rhythm so bizarre, so utterly unpredictable, that it seemed to defy everything we knew about how these objects behave. Pulsars are cosmic metronomes, their signals precise enough to rival atomic clocks. Yet here was one apparently breaking the rules, flickering on and off like a faulty light bulb. The discovery sent shockwaves through the astronomy community. Had they stumbled upon a new class of pulsar, a celestial object governed by physics we didn't yet understand? Teams scrambled to observe it, theories flying about exotic matter, hidden companions, even alien megastructures. Then came the revelation: the telescope's internal clock had been drifting. Just a tiny hiccup, barely noticeable in most observations, but pulsars are so exquisitely timed that even a millisecond error can make their signals appear chaotic. What seemed like a cosmic anomaly was in fact a mundane technical glitch. Yet this accidental find taught scientists something profound. Our tools are so sensitive that the tiniest malfunctions can mimic the universe's greatest mysteries. It forced a sobering question: how many other pulsars have we dismissed as noise because their strangeness didn't fit our models? The incident led to tighter calibration protocols, but it also sparked a new appreciation for the outliers. Sometimes the most valuable discoveries aren't the anomalies we detect, but the ones we might be missing. And in a universe full of wonders, that's a reminder worth keeping close. Of all the cosmic mysteries born from telescope errors, few have captured imaginations quite like the star that seemed to be hiding an alien megastructure. It began with a routine data dump from the Kepler Space Telescope, until astronomers noticed something bizarre about a star called KIC 8462852. Its light dimmed in irregular, dramatic dips, sometimes by as much as 22%. No natural phenomenon we knew of could block that much starlight. Planets too small, dust clouds too inconsistent. The patterns were so strange that one astronomer famously suggested we might be looking at a vast artificial construction, a so-called Dyson swarm built by an advanced civilization to harness the star's energy. The internet erupted, headlines screamed about alien megastructures, and for once, scientists didn't immediately dismiss the idea. The data was that peculiar. But as more telescopes turned toward the star, the plot thickened. Some observations revealed the dimming might be caused by uneven dust clouds or swarms of comets. Others pointed to potential calibration errors in Kepler's instruments. The star's own flickering behavior added to the chaos. Sometimes it behaved normally, only to plunge into another series of inexplicable dips. What makes this case so fascinating isn't just the initial error or the wild theories it spawned. It's the way this star refused to fit neatly into any box. Even after years of study, no single explanation fully accounts for its behavior. The dust theory, plausible, but why does the dust distribution look nothing like anything else we've seen? Instrument error, possible, but why do other telescopes still catch anomalies? The truth might be a mix of factors: natural phenomena we don't yet understand, combined with quirks in how we observe them. And that's the real lesson here. Sometimes a telescope glitch doesn't just lead us astray. It forces us to question what we think we know. KIC 8462852 isn't just a cautionary tale about jumping to alien conclusions. It's a reminder that the universe is full of phenomena we haven't even imagined yet. The star remains under watch, its secrets still unfolding. Maybe one day we'll find a mundane explanation. Or maybe, just maybe, we'll uncover something even more extraordinary than a megastructure, a natural wonder stranger than anything we could have dreamed up on our own. The universe has a way of playing tricks on us, especially when we think we've uncovered its oldest secrets. Take the case of the so-called cosmic echo that turned out to be nothing more than telescope interference. It started with a tantalizing signal, a faint ripple in the data that seemed to match predictions of gravitational waves from the Big Bang itself. For a brief, electrifying moment, astronomers believed they'd captured the faint whisper of the universe's birth, a direct echo from the dawn of time. The implications were staggering proof of cosmic inflation, a window into the first fractions of a second after creation. But then the bubble burst. The signal wasn't from the early universe at all. It was interference, a subtle artifact caused by microscopic dust particles bouncing off the telescope's electronics. The same instrument designed to listen for the faintest cosmic whispers had inadvertently recorded its own mechanical hum. The revelation was a gut punch to the scientific community, but it also became a pivotal lesson in humility. Extraordinary claims, as they say, require extraordinary evidence, and that means cross-checking with multiple instruments, ruling out every possible terrestrial explanation before declaring a cosmic breakthrough. Yet, even in its failure, this false echo revealed something profound. The fact that a simple technical glitch could so perfectly mimic a primordial signal raises an unsettling question: how many other cosmic whispers have we dismissed as noise? Or worse, how many might we have misinterpreted? The universe is a noisy place filled with background radiation, magnetic fields, and countless sources of interference. Untangling the real from the artificial is like listening for a single voice in a crowded stadium. This incident didn't just expose a flaw in our tools, it exposed a gap in our methods. Today, teams use arrays of telescopes to verify signals, ensuring no single instrument's quirks can masquerade as a cosmic revelation, but the deeper lesson lingers. Every time we peer into the cosmos, we're not just observing the universe, we're also wrestling with the limitations of our own technology. And sometimes, the most illuminating discoveries aren't the signals we find, but the illusions we learn to see past. Sometimes the universe doesn't just hide its secrets, it actively plays games with us. Take the case of the vanishing exoplanet, a world that blinked out of existence the moment scientists tried to take a second look. At first, everything seemed perfect. Data from the Kepler Space Telescope revealed a tantalizing signal, a slight, rhythmic dimming of a distant star, the telltale sign of an orbiting planet. Preliminary estimates suggested it was roughly Earth-sized, nestled snugly in the star's habitable zone, the kind of discovery that makes astronomers lean forward in their chairs. Then came the gut punch. When other telescopes swung into action to confirm the find, the planet was gone, not just hidden, erased, as if it had never existed at all. The mystery gnawed at researchers until they traced the culprit to something painfully mundane, a software bug. The telescope's targeting system had misaligned by a fraction of a degree, just enough to create the illusion of a planet where none existed. A cosmic mirage conjured by a single line of faulty code. At first glance, it might seem like a simple case of technology failing, but the implications ran far deeper. This wasn't just about one phantom planet. It forced astronomers to confront an unsettling possibility. How many other worlds had they missed because of similar errors? How many potentially habitable planets had been dismissed as noise or glitches, lost in the vast sea of data? The silver lining: this vanishing act became a catalyst for change. Scientists overhauled exoplanet detection algorithms, adding layers of verification to catch these digital illusions before they could masquerade as discoveries. Today's planet-hunting telescopes now cross-check their targets with military precision, accounting for everything from software hiccups to cosmic rays that might skew the data. But the bigger lesson remains. Every error, every false signal is a reminder of how fragile our window into the cosmos really is. Even our most advanced instruments are only as reliable as the code that guides them, and the scientists wise enough to question their own results. So while the vanishing exoplanet turned out to be a ghost, its legacy is very real. It taught us to look twice, to question everything, and to remember that in the hunt for other Earths, sometimes the most important discoveries aren't the planets we find, but the mistakes that show us how to find them better. There's something almost poetic about the way the universe mirrors our own imperfections. Take the case of the black hole that seemed to dance. Astronomers were stunned when data revealed a supermassive black hole at the heart of a distant galaxy, apparently moving in wild, erratic patterns. Black holes, especially ones this colossal, are cosmic anchors. They don't wobble, they don't zigzag, and yet here was one doing both, as if tugged by invisible strings. The implications were staggering. Could some unknown force, dark energy, hidden dimensions, even the fabric of spacetime itself, be yanking this black hole off kilter? Theories flew, each more exotic than the last. Until the truth emerged, the telescope's mount had developed a tiny, intermittent vibration. A shudder so slight it went unnoticed during routine checks, but enough to send the black hole's image skittering across the data like a pebble tossed onto a frozen pond. What's fascinating isn't just the error itself, but how it reshaped our approach to studying the universe's most enigmatic objects. That mechanical tremor, barely the width of a human hair, mimicked a phenomenon that would have rewritten astrophysics. It forced scientists to confront a humbling reality. Even the most stable instruments are at the mercy of Earth's vibrations, temperature shifts, even the faint hum of nearby electronics. But here's where the story turns from frustration to innovation. Researchers didn't just fix the mount, they designed entirely new stabilization protocols, using machine learning to distinguish between cosmic motion and terrestrial tremors. Today, those methods help telescopes filter out everything from subway rumbles to ocean tides, sharpening our view of black holes to unprecedented clarity. Yet the mystery lingers. If a shaky tripod could mimic a dancing black hole, could real black holes exhibit movements we've dismissed as noise? Some theorists now wonder if a fraction of these glitches might actually be clues, hints of black holes nudged by unseen companions or swirling in turbulent gas clouds. It's a reminder that errors don't just obscure the truth. Sometimes they point to deeper questions we hadn't thought to ask. After all, the universe is under no obligation to behave predictably. And if history's taught us anything, it's that the line between equipment failure and cosmic revelation is thinner than we dare admit. So while the dancing black hole turned out to be a mechanical hiccup, its legacy is anything but mundane. It proved that even our tools' imperfections can lead to breakthroughs, not by showing us what's out there, but by revealing how much we still have to learn about the delicate art of seeing. Imagine watching a star explode not once, but twice in rapid succession, like a cosmic light switch flickering on and off. That's exactly what astronomers thought they'd witnessed when a telescope captured what appeared to be an impossible supernova. The data showed a brilliant flare followed by an eerie pause, then another identical burst just days later. Supernova don't do that. These cataclysmic explosions are supposed to be one-and-done events, the final, violent death throes of a star. Yet here was the unthinkable, a celestial firework repeating itself as if rewound and replayed. The discovery sent theorists scrambling. Could some stars detonate in stages? Was this evidence of exotic physics, like a zombie star reigniting its own ashes? The implications were staggering until the truth emerged. The double flash wasn't a cosmic anomaly at all. A glitch in the telescope's image processing software had split the supernova's light into two artificial peaks, creating the illusion of a second explosion. The error was subtle, a rounding quirk in the algorithm that handled brightness measurements, but its effect was profound. For weeks, astronomers debated a phenomenon that didn't exist, their theories stretching to explain a ghost in the machine. At first glance, this might seem like just another case of technology tripping over itself, but the real story here isn't the mistake, it's the door it accidentally kicked open. The incident forced scientists to confront a tantalizing question: could a supernova ever repeat? Normally, the answer is a firm no, but what if the star wasn't completely destroyed? Some models suggest certain supernova might leave behind ultra-dense cores that briefly reignite, or that companion stars could trigger secondary explosions. These ideas were once dismissed as fringe, but the phantom double flash gave them unexpected legitimacy. Suddenly, researchers were dusting off old papers and running new simulations, not to debunk the error, but to ask, what if nature could produce something like this? That's the irony of this discovery. By mimicking the impossible, a software bug revealed gaps in our understanding. It showed how easily we might mistake a technical artifact for a cosmic breakthrough, but also how those mistakes can highlight genuine mysteries we've overlooked. Today, telescopes use redundant systems to catch such errors before they spark wild theories. Yet the legacy of the double flash supernova lives on. It taught us that even our failures can illuminate the universe's secrets, not by showing us what's there, but by revealing what we don't yet know. And in a field where the line between artifact and revelation is razor thin, that's a lesson worth repeating. The cosmos loves a good ghost story, and few are stranger than the case of the satellite that came back from the dead. Astronomers monitoring deep space radio signals suddenly detected familiar pulses from an object that should have been silent. A decades-old satellite, long since deactivated and drifting as space junk. The transmissions matched its original frequency perfectly, as if the relic had spontaneously rebooted. Panic rippled through space agencies. Could this derelict somehow still be operational? Worse was its erratic orbit causing interference with active missions. The implications were chilling. Space debris already poses enough risks without zombie satellites mysteriously reactivating. Teams scrambled to investigate, only to uncover a far more mundane yet equally fascinating explanation. The signals weren't coming from the satellite at all. They were echoes, a phantom chorus created when the telescope's own radio waves bounced off the satellite's metal husk and circled back to the receiver. Like a cosmic ventriloquist, the dead satellite appeared to speak, while the real source was the telescope itself. At first, the discovery felt like a letdown, just another case of human error muddying the waters of science. But this false alarm sparked a revolution in how we monitor orbital clutter. Before this incident, nobody realized how easily defunct satellites could mimic active ones simply by reflecting signals. Now, tracking systems account for these electronic mirages, filtering them out to prevent false collisions alerts or communication blackouts. Yet the deeper question lingers. If a piece of space junk could impersonate a functional satellite so convincingly, how often do we mistake other human-made noise for cosmic phenomena? Radio telescopes scan the skies for alien signals, but Earth's orbit is crowded with satellites, space debris, and even stray Wi-Fi interference. Each one adds static to the universe's soundtrack, making it harder to hear genuine extraterrestrial whispers. The zombie satellite incident didn't just expose a tracking flaw, it reminded us that every time we listen to the cosmos, we're also hearing our own technological echo. Here's the twist: some scientists now wonder if these reflections could be repurposed. Instead of dismissing them as noise, could we use satellite echoes to map orbital debris more precisely? Early experiments suggest these ghost signals might help track otherwise invisible fragments, turning a problem into a solution. That's the beauty of scientific errors. They don't just correct our course. Sometimes they reveal entirely new paths forward. So while the zombie satellite was just an illusion, its legacy is very real. A sharper, smarter approach to untangling the universe's signals from our own electronic shadow. Science thrives on those rare moments when a discovery seems to stitch together loose threads of understanding, which makes the case of the cosmic missing link that wasn't so deliciously ironic. Astronomers had long theorized about transitional galaxies, celestial objects caught mid-metamorphosis as they evolved from one type to another. So when a faint, blurry object appeared in telescope data, perfectly positioned between two known galaxy classifications, excitement skyrocketed. Here at last was the smoking gun, a cosmic intermediary caught in the act of transformation. Papers were drafted, press releases prepared, until someone noticed the galaxy moved ever so slightly between observations. Not in the way celestial objects drift across the sky, but in the way a speck of dust drifts across a lens. The revelation was equal parts hilarious and humbling. That groundbreaking missing link, just a smudge, likely a fleck of grease or a fingerprint left during maintenance. But what's remarkable isn't the mistake itself, it's how this cosmic fake-out reshaped astronomy. Before this incident, telescope optics were cleaned on loose schedules, often only when image quality visibly degraded. Now, teams treat lenses like surgical instruments, with meticulous protocols to eliminate even micron-sized contaminants. The irony is thick. A fleck of human carelessness inadvertently sharpened our view of the universe. Yet the story doesn't end there. This phantom galaxy sparked a deeper conversation about what might be slipping through the cracks. If one dust particle could mimic a theoretical missing link, how many real transitional galaxies have we dismissed as artifacts? Modern surveys now employ AI to distinguish between optical illusions and genuine oddities, flagging anything that behaves too perfectly between frames. And here's the twist: some of those flagged objects have turned out to be legitimate cosmic hybrids, galaxies caught mid-evolution after all. So while the original missing link was a mirage, its legacy is anything but illusory. It taught us that the universe's greatest secrets might be hiding not in the clear signals, but in the anomalies we've trained ourselves to ignore. And sometimes it takes a smudge on a lens to remind us that the line between artifact and discovery isn't just about cleaner optics, it's about learning to see differently. Some discoveries don't just bend the rules, they appear to shatter them entirely. Take the baffling case of the quasar that seemed to pulse in reverse, its signal playing out like a cosmic tape rewinding. Quasars, those brilliant beacons powered by supermassive black holes, are already among the universe's most extreme phenomena, but this one defied logic. Data showed its energetic outbursts unfolding backward, flares fading into existence, radio waves shrinking rather than expanding, as if time itself had flipped direction around this distant object. For a thrilling moment, astronomers dared to wonder, had they stumbled upon evidence of time reversed physics in the wild? The implications were staggering. Theoretical models had long speculated about regions where time might behave oddly near black holes, in hypothetical wormholes, or at the boundaries of exotic matter. But no one expected to see such effects mirrored in the steady rhythm of a quasar's pulses. Papers were drafted exploring wild possibilities, gravitational time loops, quantum entanglement across epochs, even echoes from a parallel universe where causality ran opposite to ours. Then came the anticlimax. The reverse pulses weren't cosmic at all. A bug in the data processing algorithm had inadvertently flipped the timestamps, turning a perfectly ordinary quasar into a time-defying enigma. Yet the story doesn't end with a simple debunking. This glitch did something remarkable. It forced physicists to confront how little we truly understand about time's behavior under extreme conditions. Sure, this particular quasar wasn't breaking the laws of physics, but could such a phenomenon exist? Some theorists argue that under rare circumstances like near a spinning black hole warping space-time, energy might appear to flow backward from our perspective. Others suggest quantum anomalies or high-dimensional physics could produce similar illusions. The glitch became a catalyst, pushing researchers to refine models and design new experiments to test time's flexibility in ways they hadn't considered before. What makes this era so fascinating isn't just the momentary confusion it caused. It's the way it exposed a gap in our cosmic intuition. We're so accustomed to time's arrow flying straight that any deviation feels impossible. But the universe owes us no such guarantees. If a simple software hiccup could mimic time reversals so convincingly, how many genuine anomalies have we dismissed because they clashed with our expectations? Modern telescopes now run dual processing systems to catch timestamp errors, but the deeper question lingers: are we filtering out the universe's true oddities alongside our own mistakes? Perhaps the greatest legacy of this time-traveling quasar is the humility it inspired. It reminded us that even our most careful observations are interpretations filtered through layers of technology, mathematics, and human bias. And in that space between raw data and understanding, there's always room for the universe to surprise us. So while this quasar wasn't rewriting physics, it did something just as valuable. It kept the door open for the next discovery that might. One of the most chilling moments in planetary defense wasn't a near miss with an asteroid. It was the moment an asteroid disappeared from view entirely. Picture the scene: astronomers tracking a sizable near-Earth object, calculating its trajectory, when suddenly their screens go blank. No technical malfunction, no interference, just empty space where the asteroid should have been. For a heart-stopping window of time, it appeared a city-sized rock had literally vanished from the sky. Emergency protocols kicked in, observatories worldwide scrambled to relocate it, and worst-case scenarios flashed through scientists' minds. Had their initial trajectory been catastrophically wrong? Was the asteroid on an unexpected collision course? The truth, when it came, was both a relief and a wake-up call. The asteroid hadn't moved. The telescope's tracking software had glitched, losing the object's trail like a dropped GPS signal. A routine system update had introduced a bug that misaligned the tracking mechanism by a fraction of a degree, just enough to let the asteroid slip from digital view. While engineers fixed the error within hours, the implications lingered. This wasn't just a technical hiccup, it was a dress rehearsal for a nightmare scenario. What if the next vanishing act wasn't a glitch, but a real asteroid veering off predicted paths? Current systems monitor thousands of near-Earth objects, but as this incident proved, even the most advanced tech is only as reliable as its weakest line of code. The silver lining: this false alarm became a catalyst for change. Astronomers overhauled tracking algorithms to include redundancy checks, ensuring no single software failure could lose an asteroid again. New protocols now cross-reference observations across multiple telescopes within seconds, creating a digital safety net. But the deeper concern remains: space is vast, and our window into it is narrow. For every asteroid we track, countless others lurk undetected, their orbits unknown. The unsettling reality is that some invisible asteroids aren't software ghosts, they're real objects slipping through observational gaps. This incident did more than expose a technical flaw. It redefined our approach to planetary defense. Today's collision monitoring systems don't just look for asteroids, they also watch for the absence of them, flagging any discrepancies that might signal a tracking error. It's a paradoxical lesson. Sometimes the most important thing we can detect isn't an object, but the shadow of our own uncertainty. And in that shadow, we're reminded just how fragile our cosmic vigilance really is. There's something hauntingly beautiful about the idea of the universe singing, and for a brief, electrifying moment, astronomers thought they'd found proof. Deep in the static of radio telescope data, a signal emerged unlike anything they'd heard before. A neutron star, one of those ultra-dense stellar corpses left behind after supernova, seemed to be pulsing in a rhythmic, almost musical pattern. Not the usual metronomic clicks of a pulsar, but something closer to melody with rises and falls that felt eerily deliberate. The discovery sparked immediate fascination. Could a dying star's magnetic fields or vibrations create something resembling music? Was this the universe's way of whispering in a language we'd never thought to listen for? Then came the letdown. The song wasn't coming from the neutron star at all. It was interference, a radio tower on Earth, its signal bouncing through the atmosphere and into the telescope's receivers. The poetic truth, the tower was broadcasting weather updates, its repetitive tones accidentally mimicking cosmic rhythms. At first glance, it was just another case of human noise polluting the scientific process. But here's where the story takes a turn. Instead of dismissing the error, scientists and artists teamed up to ask a deeper question. If a radio tower could fool us into hearing music in the stars, might the cosmos actually produce harmonies of its own? The answer, it turns out, might be yes. Neutron stars may not sing in the way we imagined, but they do vibrate, their surfaces rippling with starquakes that could theoretically be translated into sound. Black holes, when they collide, send out gravitational waves, ripples in spacetime that, if scaled up to audible frequencies, produce eerie chirps and thuds. Even the plasma waves swirling around planets like Saturn create detectable oscillations, a symphony of charged particles dancing to the pull of magnetic fields. What began as a technical glitch became a gateway, inspiring entire fields of study dedicated to sonifying cosmic phenomena, turning raw data into something our ears can interpret. Perhaps the most profound legacy of the singing neutron star is the way it blurred the line between science and art. Composers now use real astronomical data to create otherworldly music, while researchers employ sound to identify patterns in datasets too complex for the eye alone. It's a reminder that sometimes the universe's greatest gifts aren't the truths we uncover, but the new ways of listening it inspires, and who knows? One day, we might tune our instruments well enough to hear the cosmos not as static, but as the grand, uncharted symphony it's always been. 13th on our list of cosmic blunders is a particle so energetic, so baffling, it earned the nickname the ghost ray, until scientists realized the ghost was in the machine. It started with an alert from a cosmic ray observatory, detecting a single particle carrying unfathomable energy, millions of times more powerful than anything our largest particle accelerators can produce. But here's what really sent chills down researchers' spines. This cosmic bullet appeared to come from nowhere. Telescopes scanned the patch of sky it supposedly originated from, finding no supernova, no active galaxy, not even a wisp of interstellar gas that could have accelerated it to such extremes. For a fleeting moment, physicists dared to dream they'd found evidence of something beyond our models, dark matter annihilation, perhaps, or a defect in spacetime itself. Then came the plot twist. The observatory's directional sensors, those ultra-precise instruments meant to trace cosmic rays back to their sources, had been nudged out of alignment by a passing thunderstorm. The storm's pressure waves subtly warped the telescope's frame, skewing its readings just enough to point astronomers toward empty space. What seemed like a particle from the void was, in fact, a mundane case of bad weather interfering with good science. But here's where the story gets interesting. This glitch didn't just expose a technical flaw, it exposed a gap in our understanding of the universe's most energetic events. Cosmic rays at these energies are rare, and every one we detect is a clue to the universe's most violent processes. But if a misaligned sensor could send us chasing ghosts, how many real ultra-high energy particles have we dismissed because their origins didn't fit expectations? Some theorists now speculate that a fraction of these mystery cosmic rays might come from sources we've yet to imagine: primordial black holes evaporating, cosmic strings vibrating, or even collisions in hidden dimensions. The ghost ray's legacy isn't just a lesson in calibration. It's a reminder that the cosmos might be hurling more surprises at us than our instruments are designed to catch. Today, observatories use seismic monitors and real-time atmospheric corrections to avoid similar misdirection. But the bigger question remains: are we filtering out the universe's strangest signals by assuming we know where they should come from? Sometimes the most valuable errors aren't the ones we fix, they're the ones that force us to reconsider what we're not seeing. And in the hunt for physics' greatest mysteries, that might be the most haunting realization of all. Nebulae are supposed to be the slow dancers of the cosmos, their wispy tendrils shifting over centuries, not days. So when astronomers reviewing Hubble data noticed one particular nebula apparently reshaping itself within a single week, it sent shockwaves through the astrophysics community. The images showed unmistakable changes: filaments twisting, voids opening where none existed before, like watching a celestial Rorschach test rearrange itself in real time. Theories erupted. Could some unknown force magnetic instabilities, shock waves from hidden supernova, be rewriting this nebulous structure at impossible speeds? The implications would have rewritten our understanding of interstellar physics until someone spotted the telltale seams. The transformation wasn't cosmic, it was digital. The nebula's evolution traced back to a quirk in how composite images are stitched together. Hubble captures celestial objects through multiple filters, each isolating specific wavelengths of light. Software then blends these exposures into a full-color portrait, but in this case, a glitch caused slight misalignments between filter layers, creating the illusion of motion where none existed. 1 week's blue filter might be offset by a few pixels from the next, making hydrogen clouds appear to creep across the frame. What seemed like astrophysical drama was just a rendering artifact, a cosmic game of telephone between telescope and processor. Yet this digital mirage sparked a revolution in nebula studies. If a software hiccup could mimic rapid change so convincingly, how many real nebulae might be evolving faster than our models predict? Traditional observations assumed these structures were practically frozen in time, their movements too gradual to track across human lifetimes. But armed with this accidental insight, astronomers launched new time-lapse surveys, monitoring nebulae with unprecedented precision. And the results have been startling. Some star-forming regions do exhibit subtle shifts over mere decades: gas knots dissipating, shock fronts advancing, magnetic fields reconfiguring. The pace is still nowhere near the original glitch's false alarm, but it's enough to prove nebulae aren't the static tapestries we once imagined. What began as a technical error became a catalyst for discovery, revealing that even the most serene corners of the cosmos might harbor hidden turbulence. Modern image processing pipelines now flag alignment issues before they can masquerade as breakthroughs. But the deeper lesson remains: sometimes the universe's greatest secrets hide not in the data we collect, but in the flaws that make us question what we've overlooked. And in that space between error and epiphany, whole new fields of study can bloom. The universe rarely serves up perfection, which is why astronomers did a double take when they spotted what appeared to be the cosmic equivalent of a Rorschach ink blot. A galaxy so flawlessly symmetrical, its spiral arms mirrored each other with mathematical precision, as if nature had painted one half and simply hit duplicate. Statistically, this shouldn't exist. Galaxies are messy, chaotic things, their shapes sculpted by collisions, gravitational tugs, and the random swirl of star formation. Yet here was one that seemed to defy the odds, its structure so balanced it looked almost designed. The discovery sent theorists scrambling. Could some undiscovered force, a rare magnetic field alignment perhaps, or the ghostly influence of dark matter, have sculpted this celestial masterpiece? Then came the plot twist. The Mirror Galaxy wasn't a cosmic anomaly at all. It was a clerical error, a duplicate entry in a massive astronomical catalogue. Somewhere along the data pipeline, the same galaxy had been logged twice with slight positional discrepancies, creating the illusion of a perfect twin. The truth was laughably mundane, but the implications were anything but. If a simple database glitch could mimic something as extraordinary as a symmetrical galaxy, how many other impossible finds might be hiding in plain sight, waiting to be debunked or confirmed? This accidental discovery triggered a sweeping overhaul of astronomical databases, with new algorithms to weed out duplicates and cross-reference observations. But it also sparked a deeper debate. While this particular galaxy was a data artifact, could true symmetrical galaxies exist? Most known galaxies are lopsided to some degree, their imbalances telling the story of violent mergers or uneven star birth. Yet some theorists argue that under pristine conditions, a galaxy forming in isolation, free from disruptive encounters, near perfect symmetry might emerge. The hunt is now on for these cosmic unicorns, with telescopes scanning the quietest corners of the universe for structures that balance on the knife's edge of mathematical elegance. What makes this case so fascinating isn't just the error itself, but the questions it unearthed. The universe thrives on chaos, but every so often it flirts with order. Whether through a data glitch or a genuine celestial marvel, the Mirror Galaxy reminded us that our search for cosmic perfection isn't just about cataloging what's out there. It's about learning to distinguish the universe's true wonders from the ghosts in our own machines. And somewhere between those two possibilities, perhaps we'll find something even more extraordinary, a galaxy so perfect, it makes us question whether perfection was the plan all along. Black holes aren't supposed to breathe, they're cosmic vacuum cleaners, relentlessly swallowing everything in their path. So when a telescope captured what appeared to be the event horizon of a distant black hole, rhythmically expanding and contracting, like the chest of some sleeping celestial beast, scientists knew they were either witnessing something revolutionary or staring straight into the abyss of human error. The data showed a pulse, the black hole's shadow growing larger, then smaller, in a cycle so regular it could have been timed with a metronome. Theorists scrambled. Could this be evidence of black hole oscillations, a phenomenon predicted but never seen? Or worse, was our understanding of event horizons fundamentally flawed? The implications would have rewritten textbooks until engineers traced the anomaly to something painfully ordinary, a flickering power supply in the telescope's sensors. The voltage fluctuations, barely noticeable in most observations, had mimicked a cosmic heartbeat by alternately amplifying and dimming the black hole's silhouette. What seemed like the universe's most dramatic inhale and exhale was just a capacitor on the fritz. But here's where the story pivots from frustration to fascination. This glitch didn't just expose a technical weakness, it became a Rosetta Stone for black hole behavior. The artificial breathing matched theoretical models of how real black holes might pulse under extreme conditions. Some simulations suggest that when a black hole gorges on matter unevenly, say, from a lopsided accretion disk or a stellar companion feeding it in bursts, its event horizon could exhibit subtle, periodic ripples. We've never observed this directly, but the era provided an unexpected blueprint for what to look for. Suddenly, researchers had a new lens for interpreting anomalies. Could some of the noise in black hole observations actually be evidence of these quiet cosmic rhythms? The incident spurred teams to revisit old data with fresh eyes, searching for patterns that might have been dismissed as interference. Modern telescopes now monitor their own power grids as meticulously as they track celestial objects, but the ghost of that breathing black hole lingers. It's a reminder that even our mistakes can serve as dress rehearsals for discovery, preparing us to recognize the real thing when it finally appears, and the irony is delicious. A malfunctioning power supply, of all things, might have brought us closer to understanding the universe's most enigmatic objects, because sometimes the line between error and insight isn't just blurry, it's where the next breakthrough is hiding, waiting for us to stumble into it with the right mix of curiosity and humility. Time plays strange tricks in the depths of space, but none stranger than the day astronomers witnessed a star that appeared to freeze in place. Data streaming in from a routine observation showed a distant sun's brightness locked in perfect stasis, its usual flickers and flares vanishing as if someone had hit pause on the universe itself. For a heart-stopping moment, researchers dared to wonder, had they stumbled upon a celestial anomaly where time itself ran differently? The implications were dizzying. Stars are living, breathing entities, their light constantly dancing with magnetic storms, pulsations, and eruptions. Even the steadiest have subtle rhythms. Yet here was one defying all expectations, its emissions flatlining with eerie precision. Then came the reality check. The telescope's internal clock, the precise atomic timekeeper that stamps every data point, had malfunctioned. A tiny crystal oscillator, the heartbeat of the timing system, failed mid-observation, causing the instrument to record the same moment over and over. What looked like cosmic stillness was just a digital echo, a glitch repeating one snapshot like a scratched record. At first, the revelation felt like a letdown. But this frozen star, though an illusion, cracked open a door to real mysteries. Astronomers realized their instruments had never been calibrated to detect too much stability. We're so accustomed to cosmic variability that we rarely question whether a star's unwavering light might be significant. Yet what if some objects do exhibit unnatural constancy? Theories began bubbling up, stars wrapped in exotic magnetic fields that suppress fluctuations, or ancient stellar remnants cooled to near-perfect equilibrium. Some even revisited century-old reports of too steady stars dismissed as observational errors. The glitch became a catalyst, pushing teams to refine their tools to distinguish between technical hiccups and genuine cosmic stillness. Today's telescopes now cross-check timestamps across multiple systems, but the deeper quest continues. In the quietest corners of the universe, might there be stars whispering secrets in their silence? The frozen star was a phantom, but the question it left behind is very real. When it comes to the cosmos, sometimes the most startling discoveries aren't in the chaos, but in the stillness we never thought to listen for. Comets are supposed to move with predictable grace across the sky, slow travelers on million-year journeys through the solar system. So when astronomers tracking a routine icy visitor watched it seemingly leap halfway across their field of view in minutes, the observation logs lit up with panic. This wasn't just a slight deviation. It was as if the comet had been yanked by an invisible hand, violating every law of orbital mechanics. Calculations showed the apparent speed would require impossible forces, like some cosmic slingshot had flung it faster than any natural object should move. Theories flew: gravitational anomalies, hidden propulsion, even intervention by intelligences beyond Earth. The implications were staggering until someone noticed the timestamp glitch. The comet hadn't moved at all. The telescope's imaging software had stitched together frames out of sequence, creating the illusion of a jump cut in reality. A simple buffer error made celestial motion look like magic, but here's where the story twists from technical failure to scientific gold. This digital hiccup did something remarkable. It forced astronomers to confront a question they'd rarely asked aloud. Could something actually move that fast? We're so conditioned to the stately pace of solar system objects that hypervelocity motion seems like science fiction. Yet recent discoveries of interstellar visitors like Oumuamua have proven some objects do barrel through our neighborhood at breakneck speeds, tossed across galactic distances by forces we're only beginning to understand. The teleporting comet became a catalyst. Teams began re-examining old anomalies, fleeting blips in asteroid surveys, streaks dismissed as satellite glare, asking whether any might represent real ultra-fast objects. New detection algorithms now flag anything moving faster than expected, not just slower. Some theorists even speculate about exotic possibilities: microscopic black holes zipping through the solar system, or fragments of distant supernova accelerated by shockwaves we can't yet model. What began as a software bug opened a window onto the universe's hidden speed demons, reminding us that the cosmos doesn't always obey our tidy expectations. And the irony: modern telescopes now use the comet's false leap as a calibration test. If frames can mimic motion this dramatic, what subtler illusions might lurk in the data? Sometimes the universe's greatest gifts aren't the truths it reveals, but the errors that teach us how much we've yet to see. What if the universe as we know it isn't real, just an incredibly detailed projection, like a cosmic hologram? For one dizzying moment, astronomers thought they'd stumbled onto proof. It started with a routine scan of deep space data, where researchers noticed something impossible: faint, grid-like patterns in the cosmic microwave background, the afterglow of the Big Bang itself. These patterns weren't random. They formed near-perfect pixelation, as if the fabric of reality had a hidden resolution limit. The discovery sent shockwaves through theoretical physics. Was this the smoking gun for the holographic principle? The idea that our three-dimensional universe might be encoded on a two-dimensional surface at its boundaries, like a movie projected onto a screen. The excitement was short-lived. The pixels turned out to be artifacts, glitches in the software used to visualize the data. A rounding error in the rendering algorithm had subtly warped the image, imposing artificial structure onto the universe's natural chaos. But here's where the story gets fascinating. Even after the error was exposed, physicists couldn't shake the question: what if the universe does operate like a hologram? The holographic principle isn't fringe science. It's a serious hypothesis born from black hole physics, suggesting that all the information in a volume of space might be stored on its surface like a cosmic hard drive. If true, it would mean reality as we experience it is a kind of illusion, with depth and solidity emerging from something far stranger. This accidental discovery did more than expose a software bug. It spotlighted how little we understand about the nature of reality itself. Modern physics is full of hints that the universe might not be what it seems. Black holes obey laws that suggest information is preserved on their surfaces. Quantum entanglement defies classical notions of locality, as if particles are linked through some deeper, hidden layer. Even the way space-time behaves at microscopic scales hints at a pixelated structure beneath the smooth continuum we perceive. The holographic glitch became a mirror, reflecting our own uncertainty about where the boundaries lie between the universe's true nature and the limitations of our tools. Today, teams use advanced error correction algorithms to prevent similar visualization artifacts from masquerading as cosmic revelations, but the deeper conversation endures. If a simple rendering error could mimic the signature of a holographic universe so convincingly, how would we even recognize the real thing? Perhaps the answer lies not in chasing grand anomalies, but in the quiet, persistent oddities that don't fit our models, the cosmic whispers that hint we're only seeing part of the picture. After all, the most profound truths often hide not in the data we collect, but in the glitches that make us wonder what we're missing. Dark matter is supposed to be everywhere, an invisible scaffold holding galaxies together, its gravitational grip shaping the cosmos itself. So when astronomers mapped a strange region of space where this mysterious substance seemed to vanish entirely, the discovery didn't just surprise them, it threatened to upend decades of theory. The data was startling. Measurements showed a pocket of the universe where gravitational lensing, the telltale warping of light that reveals dark matter's presence, simply wasn't happening. Stars moved as if floating free, their motions defying the need for any hidden mass. For a fleeting moment, it appeared scientists had stumbled upon the impossible, a cosmic oasis where the rules didn't apply. Then came the catch. The dark matter desert wasn't a revolutionary find, it was a calibration error. The telescope's lensing measurements had been skewed by an oversight in how it accounted for distant background galaxies. A subtle misalignment in the correction algorithms created the illusion of emptiness where dark matter still lurked, unseen. At first, the revelation felt like a dead end. But this accidental illusion sparked a far more profound conversation. If our tools could mimic the absence of dark matter so convincingly, how would we recognize a real void if one existed? The incident forced astronomers to confront a tantalizing possibility. While dark matter pervades most of the universe, could there be rare pockets where it's genuinely scarce? Some theories suggest violent cosmic events, collisions between galaxy clusters, or the explosive feedback from supermassive black holes might scatter dark matter unevenly, leaving behind sparse regions. Others speculate about exotic dark matter particles that interact in ways we don't yet understand, clumping in some areas while avoiding others. The glitch became a catalyst, pushing teams to develop more robust methods to distinguish between measurement errors and genuine anomalies. Today, telescopes employ cross-verification techniques, using everything from star motions to X-ray emissions to triangulate dark matter's presence. But the bigger question lingers. In a universe dominated by mysteries, could the greatest twist be not where dark matter is, but where it isn't? The vanishing act was an illusion, but the search for its real-life counterpart has only just begun. And in that search, we're reminded that even our mistakes can point the way to deeper truth, if we're willing to follow them into the unknown. The hunt for alien life took a bizarre turn when astronomers monitoring a distant gas giant picked up what seemed to be the universe's first Chatty moon. Radio telescopes had detected strange, pulsed signals originating not from the planet itself, but from a suspected exomoon in its orbit, a world with the right conditions for liquid water. The patterns were eerily structured, repeating in sequences that resembled mathematical progressions. For a heart-pounding moment, researchers dared to wonder, had they stumbled upon a celestial broadcast? News outlets buzzed with speculation, while scientists quietly weighed the odds of a natural explanation against the chilling alternative, that something or someone might be transmitting from that frozen, distant rock. Then reality intervened. The transmissions weren't cosmic in origin at all. A satellite, one of thousands now crisscrossing Earth's orbit, had briefly passed through the telescope's field of view, its telemetry signals bouncing off the dish's curvature in just the right way to mimic a point source light years away. The timing was uncanny. The satellite's trajectory aligned so precisely with the Exomoon's predicted position that the interference seemed to come from deep space itself. What felt like a brush with the extraordinary was, in fact, a cosmic game of telephone, with human technology whispering into the void and our own instruments mistaking the echo for a message. Yet this near miss became a watershed moment in the search for extraterrestrial intelligence. Before this incident, astronomers had protocols for filtering out Earth-based interference, but nothing stringent enough to catch something this subtle. Now, observatories employ real-time satellite tracking, cross-referencing every anomalous signal with orbital data to rule out passing spacecraft. The filters are so precise they can even account for reflections off space debris, fleeting glints that might otherwise masquerade as alien beacons. But the deeper lesson here isn't just about better signal processing. It's about the universe's cruel sense of humor, how it dangles the possibility of contact only to reveal the joke's on us. And the irony, while the talking Exomoon was a false alarm, it inadvertently proved our techniques are sensitive enough to detect a transmission from another world, if one ever comes. The tools refined in this glitch's aftermath now scour the skies with unprecedented precision, separating cosmic whispers from the ever-growing static of our own civilization. So while we haven't found aliens yet, we've learned something equally valuable: how to listen through the noise to hear the universe not as we wish it would speak, but as it truly is. Quantum mechanics and the cosmos rarely collide in ways we can see until astronomers spotted a star that seemed to flicker like a subatomic particle. Data from a high-powered telescope revealed its light behaving bizarrely, switching between discrete states almost instantaneously, as if the star itself couldn't decide how bright to be. One moment it burned steadily, the next it dimmed in sharp, discontinuous jumps, defying the smooth variability stars are known for. The discovery sent shockwaves through astrophysics. Was this the first evidence of macroscopic quantum effects in a stellar object? Could the extreme conditions inside certain stars, crushing densities, unimaginable pressures, create an environment where quantum weirdness bubbles up to visible scales? The implications were staggering, hinting at a hidden bridge between the subatomic and the cosmic. Then came the letdown. The star wasn't exhibiting quantum behavior at all. A polarizing filter in the telescope's optical path had begun to delaminate, its degraded layers subtly warping the incoming light. The effect mimicked quantum superposition, turning the star's steady glow into a series of artificial, discrete steps. A mundane malfunction had masqueraded as a revolution in physics. Yet this cosmic fake-out sparked something extraordinary. Theorists began revisiting old questions with fresh urgency. Could quantum phenomena ever manifest visibly in stars? Normally, quantum effects vanish at larger scales, drowned out by classical physics. But what about in neutron stars, where a teaspoon of matter weighs 1 billion tons? Or in white dwarfs, where electrons are packed shoulder to shoulder in a quantum dance? The glitch became a catalyst. Researchers realized that while this particular star's behavior was an illusion, the underlying question wasn't. Some exotic stellar objects might genuinely blur the line between quantum and classical realms. Take magnetar's neutron stars with magnetic fields so intense they could rip atoms apart from 1,000 miles away. Under those conditions, could quantum fluctuations imprint on the star's X-ray emissions? Or consider pulsars, whose precise beams of radiation might carry subtle quantum signatures if their surfaces behave more like condensed matter than traditional plasma. The faulty filter didn't just expose a technical flaw, it highlighted how little we understand about quantum mechanics' role in the cosmos' most extreme environments. Today, telescopes employ redundant polarization checks to avoid similar illusions, but the deeper conversation continues. The universe is under no obligation to fit neatly into our categories. What we dismiss as quantum or classical might just be limits of our perception, and sometimes it takes a malfunctioning piece of glass to remind us that the most profound discoveries aren't always the ones we make, but the possibilities we learn to imagine. Time isn't just something we measure, it's the invisible fabric stitching the universe together. So when astronomers reviewing deep space data noticed something that looked like tiny, regular gaps in the flow of time itself, the implications were staggering. The telescope had captured what appeared to be minuscule pauses in celestial events, as if the universe was running on a cosmic frame rate, ticking forward in discrete steps rather than a smooth, unbroken stream. For a dizzying moment, it seemed science had stumbled upon proof that time wasn't continuous, that it moved in indivisible increments, like pixels in the fabric of reality. The discovery ignited fierce debate. Could this be the first observable evidence of Planck time, the theoretical smallest possible unit of time at the quantum level? Or was it something even stranger, a glitch in the universe's operating system? Then came the letdown. The end-of-time anomaly wasn't a cosmic revelation. It was a quirk in how the telescope's sensors sampled data. The instrument's internal clock had been syncing with its data recorder in uneven intervals, creating artificial gaps that mimicked time itself stuttering. What seemed like the universe hitting pause was just a mundane case of digital misalignment, but here's where the story twists from frustration to fascination. This glitch didn't just expose a technical flaw, it shone a spotlight on one of physics' greatest unsolved mysteries. The idea that time might be granular isn't new. Quantum gravity theories suggest that at the smallest scales, time could behave less like a river and more like a series of still frames, with each moment lasting roughly 10 to the power of minus 43 seconds, a duration so short it makes a nanosecond feel like an eternity. If true, it would mean our perception of smooth, flowing time is an illusion, woven together by a reality that's fundamentally pixelated. The telescope's error, though accidental, gave researchers an unexpected template for what such discreteness might look like in real data. Suddenly, teams were revisiting old observations with fresh eyes, asking whether any unexplained irregularities might hint at time's true structure. What makes this debate so gripping isn't just the science, it's the philosophical weight behind it. If time isn't continuous, what does that mean for free will, for causality, even for the nature of reality itself? Some theorists argue granular time would impose a cosmic speed limit on change, like a processor cycling through updates. Others suggest it could open doors to phenomena we can't yet imagine: time crystals, quantum echoes, or even ways to manipulate time's building blocks. The telescope's glitch didn't answer these questions, but it did something just as valuable. It reminded us that the universe's deepest secrets might be hiding not in the grand phenomena we study, but in the quiet, almost imperceptible gaps between moments. Today's observatories employ redundant timing systems to prevent similar artifacts from muddying the waters, but the conversation this error sparked is far from over. As detectors grow more precise, who's to say we won't one day catch the universe mid-tick, catching time itself in the act of moving from one quantum step to the next? Until then, we're left with a tantalizing thought. Sometimes the most profound truths aren't in the signals we detect, but in the glitches that make us wonder what else we're missing between the ticks of the cosmic clock. The idea of parallel universes has long danced at the edges of scientific respectability, too tantalizing to ignore, too speculative to prove. That's why the astronomy community held its collective breath when a team analyzing the cosmic microwave background spotted something impossible: faint, concentric rings in the afterglow of the Big Bang itself. These patterns weren't random. They looked like bruises, as if our universe had collided with another in the distant past. The implications were staggering. If true, this could be the first tangible evidence of a multiverse, proof that our cosmos is just one bubble in an infinite froth of realities. Headlines erupted with claims of a breakthrough, while theorists dusted off decades-old models of bubble universes, brushing against one another in the vastness of whatever lies beyond. Then came the cold splash of reality. The bruises weren't cosmic at all. They were thermal echoes from the telescope's own cooling system, subtle vibrations in the machinery imprinting false patterns onto the data. What seemed like a window into other dimensions was just a refrigerator humming in the background. But here's where the story twists from disappointment to revelation. This false alarm didn't kill the multiverse hypothesis, it gave it new life. Suddenly, researchers had a concrete template for what a real collision might look like. The accidental patterns became a Rosetta Stone, helping teams refine their searches and filter out earthly interference. The incident also exposed a deeper truth. Our hunt for parallel universes isn't just limited by imagination, but by the astonishing precision required to detect them. Think about it. If a telescope's cooling system can mimic the signature of a universe next door, what hope do we have of spotting the real thing? The answer lies in next-generation instruments, like space-based observatories shielded from Earth's thermal noise, or quantum sensors so sensitive they could distinguish between cosmic whispers and mechanical shudders. Some teams are even developing AI that can listen for multiverse echoes in old data, searching for anomalies that earlier astronomers might have dismissed as glitches. What makes this search so electrifying isn't just the science, it's the philosophical stakes. Confirming the multiverse would rewrite our understanding of reality itself. Are those faint patterns in the cosmic background just noise, or the fingerprints of another universe nudging against ours? For now, we're left with a tantalizing paradox. The same errors that lead us astray might also be guiding us toward truths we're not yet equipped to see. And in that tension between human fallibility and cosmic possibility, the most extraordinary discoveries often wait. What if a planet could breathe? Astronomers thought they'd found exactly that when data revealed a distant world's atmosphere shifting before their eyes, its chemical makeup transforming dramatically over mere weeks. One observation showed methane spikes consistent with microbial life. The next, oxygen levels flaring as if the planet itself was exhaling. The implications were staggering. No known geological process could explain such rapid changes. Was this the first whiff of alien biology, a planetary metabolism playing out on a scale we'd never imagined? The excitement was palpable until engineers traced the anomaly to a spectrograph's calibration drift. The instrument, designed to dissect starlight filtering through exoplanet atmospheres, had slowly skewed its readings, turning subtle measurement errors into the illusion of a living, pulsing world. Yet this cosmic mirage exposed a far deeper challenge in the hunt for extraterrestrial life. Detecting biosignatures, chemical traces of biology, requires near-perfect precision. A misaligned sensor might mistake methane for carbon dioxide, or confuse volcanic sulfur with the byproducts of photosynthesis. The line between groundbreaking discovery and equipment failure is razor thin. Consider the stakes. If a simple calibration error could mimic the signs of a breathing planet, how many genuine biospheres have we overlooked because their signals fell into the noise? Some researchers now suspect our catalogues of lifeless worlds might hide false negatives, planets dismissed as barren due to glitches we didn't catch. The incident sparked a revolution in observational protocols. Modern telescopes now perform real-time calibration checks using laser frequency combs to anchor their measurements to atomic standards. But the philosophical question lingers. In a universe where our tools can so easily conjure phantom biospheres, how do we distinguish the real thing? The answer might lie in redundancy, combining multiple detection methods, from atmospheric spectroscopy to direct imaging, to build a case no single error could fake. Perhaps the greatest lesson of the living planet isn't about our instruments' flaws, but about nature's creativity. If a malfunction can mimic life so convincingly, what wonders might real alien biospheres produce? The cosmos rarely follows our scripts. The next true biosignature might not be a tidy chemical ratio, but something wilder, stranger, a pattern only unmistakable once we've learned to see past our own reflections in the data. And that's the ultimate irony. Sometimes the errors that lead us astray are the very things that teach us how to recognize the truth when it finally appears. There's something achingly human about the way we search for meaning in the stars, a habit that reached its peak when astronomers intercepted a signal so perfectly patterned, it seemed to whisper of intelligence. The pulses arrived like clockwork, repeating in a sequence that mirrored prime numbers, a mathematical fingerprint many considered the universal language of advanced civilizations. For a breathless moment, the world dared to wonder, had we finally intercepted a cosmic hello? The implications were dizzying. Here was a signal that didn't just exist, it communicated. Its structure so deliberate it felt like a hand reaching across the void. Theorists raced to decode it while skeptics scrambled for natural explanations. Then came the crushing revelation. The message wasn't extraterrestrial at all. It was the telescope's own transmission system short-circuiting, its malfunctioning electronics generating a loop of artificial pulses that, by sheer cosmic coincidence, mirrored what we'd expect from an alien broadcast. The irony was almost poetic. In our eagerness to find order in the chaos of the universe, we'd mistaken the hum of our own machines for the voice of the cosmos. But this glitch did more than disappoint. It exposed a fundamental truth about how we explore the unknown. Humans are pattern-seeking creatures, wired to find faces in clouds and meaning in static. It's how we've survived, how we've built civilizations. Yet that same instinct can lead us astray, dressing up randomness in the cloak of intention. The cosmic code wasn't just a technical error. It was a mirror, reflecting our desperation to believe we're not alone in the universe. What makes this case so fascinating isn't the mistake itself, but the questions it forces us to confront. If a faulty circuit can mimic an alien signal so convincingly, how many genuine cosmic messages have we dismissed as noise? Modern SETI programs now account for this bias, using AI to distinguish between human-made interference and signals that defy earthly explanation. But the deeper challenge remains: the universe doesn't owe us clarity. Its true messages might not arrive as neatly packaged prime numbers or flashing beacons. They could be subtle shifts in stellar spectra, anomalies in quantum fields, or patterns so alien we lack the framework to recognize them. Perhaps the greatest lesson of the cosmic code is humility. The cosmos speaks in a language older than thought, and we're only beginning to learn its grammar. Our tools will fail, our biases will blind us, but the search continues not because we expect easy answers, but because the universe, in all its mystery, is too compelling to ignore. And who knows, one day, amid the noise of our own imperfections, we might just stumble upon a signal that doesn't have a human source. Until then, we're left with a paradox. The very errors that lead us astray are the ones that teach us how to listen. Behind every telescope error lies an unspoken truth. Science advances not just in spite of mistakes, but because of them. These 26 cases aren't just catalogs of human fallibility, they're masterclasses in how discovery really works. When a software bug mimics a galaxy or a jittery mount impersonates a dancing black hole, it forces researchers to confront the limits of their tools and their own assumptions. Take the phantom exoplanet that vanished due to a targeting glitch. That single mishap revolutionized how astronomers validate new worlds, adding layers of redundancy to ensure no real discovery slips through the cracks. Or consider the cosmic ray that wasn't. Its apparent origin in the void exposed how even microscopic sensor shifts can send us chasing ghosts. Each error became a mirror, reflecting blind spots in our cosmic vision we didn't know existed. What's striking isn't just how often these glitches occurred, but how they consistently pointed toward deeper mysteries. The breathing black hole artifact didn't just reveal a faulty power supply, it matched theoretical models of how real black holes might pulse under extreme conditions. The malfunction became a roadmap, guiding scientists to refine their search for genuine astrophysical rhythms. Similarly, the frozen star illusion, born from a broken atomic clock, sparked new discussions about whether certain stellar objects might exhibit unnatural stillness. These accidents did more than correct technical protocols. They expanded the boundaries of what astronomers considered possible. The true value of these errors lies in their paradox. They remind us that our view of the cosmos is always filtered through imperfect instruments, fallible software, and human biases. Yet by studying where those filters distort reality, we learn to see more clearly. Modern telescopes now hunt for evidence of granular time, not because the original stuttering universe glitch was real, but because it highlighted how little we understand time's fundamental nature. The holographic universe artifact, though debunked, refined our search for quantum signatures in the cosmic microwave background. Even the talking Exomoon hoax upgraded SETI signal processing algorithms to heights no one had previously thought necessary. Perhaps the most profound lesson is this: scientific progress isn't a straight path from question to answer. It's a spiral where each wrong turn, each dead end, forces us to redraw the map. The next groundbreaking discovery might not announce itself with fanfare. It could lurk in the static between signals, in the outlier date of points we've been trained to ignore, or in another era waiting for someone bold enough to ask, what if this isn't a mistake at all? After all, the universe doesn't play by our rules, and sometimes it's only when our tools fail that we finally glimpse the truth they've been hiding. From phantom galaxies to talking exomoons, these 26 accidental discoveries prove that even mistakes can illuminate the cosmos in ways we never anticipated. Each glitch, each false alarm, became a masterclass in scientific humility, reminding us that the universe doesn't reveal its secrets easily. Think about it, without these errors, would we have questioned how pulsars might pulse under extreme conditions? Would we have refined our tools to hunt for cosmic stillness or quantum echoes in starlight? The beauty of these mishaps isn't just in the corrections they inspired, but in the doors they kicked open. They forced us to confront the uncomfortable truth that our telescopes don't just show us the universe, they filter it through layers of human engineering, software, and sometimes pure blind luck. But here's the twist: as technology improves, the line between error and revelation grows even thinner. Next-generation telescopes peer deeper into space with sensors so sensitive, A single cosmic ray or a flickering capacitor can mimic phenomena that would have been unimaginable a decade ago. The irony is delicious. The better our instruments become, the more creative the universe gets at fooling us, and yet that's where the magic happens. Every glitch that sends scientists scrambling to double-check their data, every phantom signal that sparks a debate, is a testament to how much we still don't know. The cosmos thrives on mystery, and these accidental discoveries are its way of keeping us on our toes. So what's next? Perhaps a telescope malfunction will reveal a hidden dimension, or a software bug will expose a flaw in our understanding of dark energy. Maybe the next great cosmic breakthrough won't come from a flawless observation, but from someone brave enough to ask, what if this error isn't an error at all? That's the thrill of exploration. The universe's greatest truths might be hiding in plain sight, disguised as mistakes until someone looks at them just right. Which of these cosmic blunders fascinates you the most? Was it the black hole that seemed to breathe, or the star that flickered like a quantum particle? Drop your thoughts in the comments, and don't forget to subscribe for more deep dives into space's greatest enigmas. After all, the next unthinkable discovery could be waiting in the static of a faulty signal, the tremor of a telescope mount, or the quiet hum of a machine whispering secrets we're only beginning to understand. The universe is full of surprises, and sometimes the best way to find them is to embrace the happy accidents along the way.